All right, let me check. Can everybody hear me first? Can you just thumbs up? Good? All right. So I'm going to talk about robustRL. I'm sure most of you don't know what it's about. But hopefully in an hour or so, you'll all have a better idea. So I'm going to actually bring together several of the streams we've seen before. I'm going to talk about model-based RL. I'm going to talk about sample efficiency. I'm going to talk about optimization. I'm going to talk about off-policy evaluation, all in one package. A lot of what you're going to see is going to be a little bit different flavor from what we've seen so far, but hopefully you guys appreciate it and get a little bit of a different perspective on these problems. So I'd like to keep this interactive. Please don't be afraid to ask questions, or I'll have some questions for you guys to answer as well. All right, how many people have seen a picture like this before? Cool, right. So this is not from RL. This is actually from regular deep learning. So the idea is here that we have these really cool deep learning models. They can learn very impressive concepts from big data sets. They can do really, really well when we test them on the test sets. However, if you take this picture of a pig, your model is going to predict that it is a pig with high percentage, high probability, high confidence. And it turns out that if you add a little bit of a noise, you can confuse many of these deep learning systems. Now, how many people think that what you see here on the right-hand side is an airplane? Nobody, right? We humans are pretty robust. We humans can look at pictures, and it's very hard to confuse us with a little bit of a random noise. But it turns out a lot of the machine learning techniques are not that robust. Now, the question is this something we need to worry about? Is this a problem? What do you think? Yes. Why is this a problem? Why do we need to worry about this? Attacks. What does it mean? Yeah, so we need to worry about security. We need to worry about adversaries adding a little bit of a noise to our data, which could be either adding noise to a picture in medical imaging. It can be as simple as adding a sticker to a stop sign. And now your autonomous car is not going to think it's a stop sign. It's going to think it's a 90 miles per hour speed limit. All right? Any other issues? Yeah? The real world is noisy, yeah? So this noise, I call it noise here, it's not really random. It's specifically constructed to fool the method. But doesn't mean you're not going to get noise like that in the real world. Any other issues? It's not learning the high-level semantics. It's not really trustworthy, right? If I tell you that your autonomous car, that you put your life, that you risk your life with, thinks that this is an airliner and it's 99% confident, are we really going to trust the system? I wouldn't. Oops, wrong direction. All right, so safety, security, trust. Now, do you think that the reinforcement learning suffers from the same issues? How many people think that it does? How many people think it doesn't? Well, if it didn't, then I wouldn't be here, and I wouldn't have asked this question, right? So I'm going to try to make the case that yes, it does suffer from similar problems, and we do have some simple methods to address that. It's a new field. Well, let me say, it's not really a new field, but we have a long way to go before these problems are solved. All right, so I'm talking about robustness, but robustness has become a buzzword, right? Like everybody wants their algorithm to be robust. Everybody talks about it. Let's actually make sure we understand what I mean by robustness. So when I say an algorithm is robust, what I really mean is that it performs well, even in the presence of small errors in the input. All right, this is still pretty vague. So what I'm going to do in this talk, I'm to answer these three questions. What does it mean that the algorithm performs well? What is a small error? And how do we actually compute this robust solution? How can we get a robust solution in reinforcement learning? So this is the outline of the talk. I'm going to kind of go backwards. First, in the first two sections, the first two parts, I'm going to give you tools that we'll need to compute these robust solutions. And then I'll go back and talk about where the robustness comes from. How do we model it? What the small errors are? And I'll conclude with some other formulations, other approaches to the problem. Now, I've said through most of the talks in the past 2 days, and it really made me kind of think about how this work fits in to the rest of what we've heard so far. So I tried to summarize this entire talk in one sentence, full of jargon, and this is it. So I'm going to talk about a model-based approach to reliable, off-policy, sample-efficient, tabular reinforcement learning. And we're going to solve the problems by learning not only models, but learning also confidence in these models. Any questions? All right, so let's start talking about adversarial robustness in RL. I'm going to start with a disclaimer. I don't think robustness always matters. You know, we've solved some really impressive problems using reinforcement learning, and nobody had to worry about robustness. You can solve awesome problems like the inverted pendulum or the card pull. You can solve Atari games, Minecraft, chess, Go, so on, and you don't have to worry about robustness. Why is that? Well, most of these problems that we solved so far are deterministic. We know the dynamics. For Atari games, it's a deterministic problems. We have a simulator. The simulator is very precise, does exactly what we want it to do, and it's also very fast. We can get lots and lots of samples. And finally, if our method doesn't work, there's very little penalty. If you compute a policy, the policy is bad, you run it on the simulator, you'll find out that it doesn't work. You'll try again. You tweak your neural net, you change your step size, you do something, and you iterate until you get a solution in the end. So the failure of learning good policy is cheap. Now, when does robustness actually matter? So I personally feel very strongly about taking RL, taking it from the lab, and trying to apply it to real-world problems, to actually solve something that people care about outside of machine learning, outside of our field. And I would argue that in many of those problems, robustness actually matters quite a bit. Often, we do not have a simulator. All we have is a data set, right? We can't run experiments easily. We just need to learn from this one data set. Now, whenever you get to a situation where you're given a data set, I've seen many, many problems, and I've never, ever seen a problem where I had enough data. So if you're given a data set, you typically, not only the data is bad, but it's also not big enough. Finally, what is really important is that once you're in this batch reinforcement learning setting, you lose a tool that's super useful in regular machine learning. You lose cross-validation. You don't have a training set. You don't have a test set. So it's really hard to tell when you compute a policy whether the policy is good or whether the policy is bad.
I've worked with a bunch of customers, and nobody's happy when you deliver a solution that you promise that works really well, and it loses your customer a bunch of money. So we need to be really careful about what kind of policies compute. And in many domains, the cost of failure can be really hard. Now, any ideas what kind of applications I may be talking about? What do you think, what kind of applications would satisfy this kind of problems? Autonomous cars, a very good example. Stock market. Stock market is one case where you actually can get lots of data usually, but yes, you can lose lots and lots of money. Medicine, yeah. So healthcare, very important. If you deliver a bad policy, people are going to die, right? You don't want that. We don't want that, right? Any other ideas?
Industrial settings, like a
Processing facility, a lot of industrial settings. Again, failures, if you deliver a bad policy, somebody's going to lose a lot of money. So these are some of the examples I've come up with. So I'm a little different from some other RL people. I have been recently working on agriculture, and I think it's a very good example where you see many of these issues. The reason is that so you want to figure out how to better, say, grow corn. You don't have a simulator. You can get data, but one episode takes 1 year. There's really no way to speed that up, right? And so you can't really iterate through different episodes in a reasonable time. It would take you 100 years. Healthcare was mentioned, maintenance, infrastructure, things like this. Again, data's difficult to get, and nobody's going to let you experiment. If you deliver a policy, you better be sure that the policy is actually pretty good. Autonomous vehicles, robotics, so on. All right, so many of the ideas I'm going to describe are kind of abstract. So I'm going to try to make it a little bit more concrete by working with this one simple example, which is motivated by some of autonomous vehicles, robotics, so on. All right, sure, I want to talk about pest management. Now, disclaimer, this is not a real problem. This is based on a real problem, but it's very highly simplified, okay? So why I think agriculture is a good reinforcement learning domain? So the environment is stochastic. Weather's very different from year to year. The rewards are really delayed. So you have to water your crop, you have to spray pesticides during the season, and you're not getting any reward until you actually harvest your crop 5 or 6 months later. As I said, one episode takes 1 year. Crop failure is expensive. Now, if you're a subsistence farmer, that could cost your life. If you're not, it could cost your farm. So you really don't want your policy to be bad. Now, I said no simulator, but I didn't want to go through all the trouble of actually growing crops to evaluate my policies. So I'm going to show you all of these results in simulation. This is a very simplified simulation based on some well-established ecological models. I'm not going to get into the details here, except to say that this is loosely based on some work we've been doing with important pest on the east coast of the United States. So we can formulate this as a simple MVP, okay? We have our states, which is the pest population. So this problem is tabular. We have only 51 states. We have 5 actions. We can use no pesticide at every decision point, or use one of 4 different pesticides with increasing efficiencies. So think of it as increasing the amount of the pesticide you use. Transition probabilities are just the pest population dynamics. The rewards are the crop yield minus pest damage. and minus spraying costs, where P4 is more expensive than P1. So let's just remind ourselves about MDPs. This is just like most of the other talks, set in the context of discounted infinite horizon rewards. I'm going to use this quantity that I called return. This is your objective. This is what you're trying to maximize. So you can think of it as the value of the initial state. Our optimal solution is going to maximize the return. An important concept we've seen a lot is the value function, which maps states into the expected return, and the Bellman optimality, which tells you that the value of any state is equal to the best action with respect to the immediate reward plus the discounted reward in the next step. Sorry, discounted value in the next step. Now let me get a sense. How many people how would you solve an MDP? What are some methods you could use to solve an MDP? If you have the model. Right now we are working with an MDP, we have a model. How do you solve an MDP? Yeah, so what are some dynamic programming methods? Value iteration is the most basic one, right? There are a couple of other very important methods which I haven't heard mentioned here. Does anybody know what they are? Good. So I'll show you a couple of them in a minute. This is just to show you a picture of the transition probabilities to get a sense of how stochastic this problem is. So these are transition probabilities for 4 of my 5 actions, where here you're looking at the population at time t, and this represents your population at t plus 1. So the more blue, the higher probability of actually transitioning to that state. So if you see, if you don't use a pesticide, if you are at population 20, it's likely that the next step, your population is going to increase quite a bit. And as you look at P1, P3, and P4, you see that the variance goes down, down, and down, because you're using more and more pesticides. So the actual dynamics are not important, but I'm going to show you pictures like this a little bit more during the rest of the talk. All right, so computing an optimal policy, solving an MDP. So people have mentioned value iteration. Value iteration is super simple, but often very, very, very inefficient. So there are many cases where you actually don't want to use value iteration to solve your MDP. Other popular methods are policy iteration, modified policy iteration, and linear programming. They can be thousands of times faster than value iteration, millions of times faster. Depends on what kind of a problem you have. So we can take this MDP, we can solve it. And this is the optimal policy. So what you see here is the state, and what this is showing is the optimal policy for the state. So what you're seeing here is that as long as your population is between 0 and 8, you're not doing anything. Once it reaches 8, you start spraying with the pesticide 1, and as the population goes up, you use more and more efficient pesticides. If your population goes over some threshold, you basically give up. You don't want to spray anymore because you're not going to save your crop anyway. So you may as well just switch to doing nothing and save money. And so that's why this is kind of a Hail Mary attempt where you just try it. If it doesn't work, you give up. Any questions? Yeah?
I was wondering about the reward. I see that the return is in cost, right? So
Oh, yeah.
if you could elaborate just a little bit more on the rewards would be negative mostly, or is there like a cost-benefit?
There's a cost-benefit. So there's a positive reward for growing a crop. As your pest population goes higher and increases, you get negative rewards for crop losses due to the pests. So think of like ears of corn that have worms in it, which you have to throw away rather than that you can sell. And you're also paying a penalty for using spraying, right?
Is there like an end goal that you might get like a big reward to go, or is
So what I did here, so the question is if there is a big reward and the goal. There's really no goal here. I spread the harvest crops through the season. This is really, so we're working with blueberries, and blueberries you kind of pick throughout the season. So in this case, there's no delayed reward. You kind of get rewards as you go along. And you're losing them as you have higher and higher pest populations. I'm not going to go into the details of the formulation, but all of that is available online, and I'll give you some pointers. I thought there was another question.
Where is that model coming from again? Sorry. Is it like in agriculture?
Yeah, so this is a model that's not this particular example, but this is based on a model. It's called the logistic population model, which is established in agriculture and ecological modeling. So there's a lot of machine learning going on in ecological models, and I have some collaborators who helped me put this together. Any other questions? All right, I don't want to spend too much time on this. This is just the optimal transitions. I'm just using this example to demonstrate what's going on. This is just an example of a simulation. So you have 40 time steps. Here you see the pest population, and the background color shows you which action you're taking. So you see if the population is really low, you just stand back, you don't do anything. And as your population goes higher and higher, you're using more and more pesticides. All right, so we had a model. We computed the optimal solution, and optimal solution earns us $8,000, right? Now, is this robust? Is it robust in the sense that if we add a little bit of an error to our model, a little bit of an error to the transition probabilities, how much money are we going to make? So these are my transition probabilities. I'm going to add a little bit of a noise. And what this means is that the noise I'm adding here, the L1 norm, think of it as the size of the noise, for each one of the states is less than 0.05. So this is a very little bit of a noise. And you see two colors here. The red means subtraction, blue means addition. So even if my model is wrong, the transition probabilities still have to sum to 1. And so unlike with the pig and the airliner example, we have to make sure that if we subtract somewhere, we're going to add somewhere else. Any guess how much money you make if the transition probabilities are perturbed by this little? It could be really anything, right? Actually, lose quite a bit. So I don't think this is kind of as silly looking as the pig and the airliner, but I think this is still a problem. And I've seen this actually happen in practice, where we delivered solutions, we promised our customers that they were going to get rich, and instead, they didn't get rich, they weren't happy. So this is not good, right? Now you could say, well, this is kind of a strange noise you're looking at. There's like one state adding, one state subtracting, and really the noise I am showing you is governed by this L1 norm. You could replace this by L infinity, by other norms. You get different noise patterns, but you get basically the same results. So I'd argue that robustness is important in RL, and if you're not robust, bad things can happen. And the thing is, you will not know about it. If you don't have a simulator, you don't really know this is going to happen until you deploy the policy. What can we do about it? We're going to do about it essentially the same thing what people do about robustness in deep learning. It turns out this is an old idea, but I think it's a very good idea, actually. So again, we want an algorithm which is robust, so it performs well even in the presence of small errors in the inputs. So we're going to look for the best policy with respect to inputs with all possible small errors. So we're going to get this max-min problem. So let's break this down. Let's see what's going on here. So return, this is how much money we're making if we follow policy pi, and if the true transition probabilities P and R are P and R. Now we're going to try to compute the best policy such that for the worst realization of the transition probabilities and rewards, we maximize the return. Now clearly we cannot just expect to get a good solution that works for any P and any R, right? There's just no way to do that. And so what we're going to do is we're going to assume that there is some nominal model, there's some P that we expect to see. And the difference, I'm using the norm in kind of an abstract sense right now, but I will make it much more concrete in a couple of minutes. We're saying that the difference between some nominal P and the P we're actually seeing is small. The difference between the nominal rewards and the actual rewards is small. So think of it as an adversarial game against nature. You're trying to optimize, you're trying to maximize. There is this nature which is playing against you. It's trying to get you rewards that are really small. Any questions about this? Yeah? No, the adversary chooses P, but it cannot choose a P that's too far away from your P bar. So P bar is like your anchor. This is the model you construct. And you want to make sure that if there's an adversary which can add a little bit of a noise to your model, your performance is still going to be pretty good. I think this is correct. There might be a typo, but I don't see it there. We'll make this more concrete, and we'll revisit that several times during the remaining hour or so. Any other questions? It could be non-stationary. We'll address that question in a couple slides. Any other questions? Now, this general approach to optimization is known as robust optimization. And so I'm using robust here to describe both the objective and the method. Now, robust optimization has been studied for many years. Actually, there are some very fundamental deep connections between robustness and regularization that I'm not going to talk about, but there's a reference here between risk, specifically coherent risk measures, and optimization. And really what I'm doing here is the opposite of exploration. You want to avoid things you're uncertain about. You don't want to go to places that you're uncertain about. All right, so let's kind of break down this problem into two subproblems. So we could be trying to be robust with respect to the rewards. The rewards are uncertain. There's this upper optimization problem. We can try to be robust with respect to transition probabilities. So let's look at the first problem first. Oh yeah, here psi, I'll be using, it's called the budget. It's the size of the error. It's how much power we give to nature. All right, so let's say we have reward functions that are uncertain. We want to be robust to the uncertainty in the reward functions. We have this max-min optimization problem. I'm saying that we want to maximize the return subject to the rewards not being too far from some R bar. And we're assuming for now that the transitions P bar are known. How would you solve a problem like this? Any ideas? Don't be afraid. Any guess is better than no guess. It's a saddle point problem. You could solve it as a saddle point problem. That's a very good guess. There's actually an easier way to solve this. I wonder if anybody is familiar with this. Yeah? You could do that. That's actually not guaranteed to give you the optimal solution. That's a very simple approach. But there is actually an approach that's even simpler, and it gives you the optimal solution. Yes?
Adding a kind of regularization sheet test, like minimizing the objective with a kind of regularization.
That's kind of what you end up with. But the reason I'm dwelling on this, that I think this is a very important technique. This is something that works for 90% of optimization problems. And I just read a paper that was published in one of the machine learning conferences recently, where they spent 8 pages trying to develop an algorithm for a problem like this. And you can really solve this in 15 minutes, including coding time. So this is an important technique, and we're going to use linear programming, right? If you don't know about linear programming, you should fix that. That's my opinion. Anybody who does machine learning should know about optimization. So the first step is to formulate this minimization problem as a linear program. So we get a max. U is the occupancy frequencies. I'm not going to go into the details. If you don't know about this, you'll probably need a couple hours to really digest this formulation. I'm just going to formulate this as a minimization problem. This is a linear program. And this is the step that works for 90% of robust optimization. It's called duality. We take this minimization and turn it into a maximization problem. You can do this for any convex optimization problem. Bam. We have a linear program. We have lots and lots of solvers that are super fast, super easy to use, super robust, that are going to solve this. Now, this problem, I don't know of any value iteration and policy iteration style algorithm that solves a problem like this in the general setting. All right, so these are the reward functions. This is a simple setting. We can solve it as a linear program. I would just say here, this is the dual norm. And what you see here is really our robustness has turned into a regularization. So we're regularizing U with the dual norm of what our errors were. And as I said, 90% of robust optimization can be solved this way. A very powerful technique. All right, let's look at the other problem. Let's say our transition probabilities are uncertain. How would you solve a problem like this? Any guesses? Using what? So one guess is linear programming. It's wrong. I said 90%, not 100. This is one of the remaining 10%. So this problem, as is stated here, is unfortunately NP hard to solve. There's no linear programming formulation for this problem. Now, don't despair. We'll look at some simplified formulations. We'll make some assumptions that will make this problem tractable. But even when it's tractable, there doesn't appear to be any convex optimization formulation for this problem, which I think is a really cool research problem if you're interested in that. I'm going to use this weird term called ambiguity set, sometimes known as the uncertainty set. And this simply represents the set of all transition probabilities that are within my threshold of the P bar. So think of this as a set of possible models you want to be robust with respect to. And really, this is the more difficult, more common of the two problems I showed you. And this is the one I'm going to dedicate the rest of the lecture to. Are there any questions? Yeah? Yes, absolutely. Has anybody really done that? Kind of. There's been a little bit of work looking at that. I think that's an important research direction, which hasn't been studied as much as it should be. We're going to address that in the second half of the talk. So save that question. So the question was about the ambiguity sets, feasible sets. We'll talk about that in 15 or 20 minutes. Any other questions? All right, so let's move on to one way of actually solving these problems, solving them quickly in polynomial time. And this is robust Markov decision processes. It's a generalization of a Markov decision process, which I think is really cool. So I wanted to have a little bit of a history lecture here, because I feel like a lot of people these days feel like there's nothing interesting that was done before 2015, right? That's not really true. And I've worked on this robust optimization problem for many years, and the longer I work, the farther and farther in time I find references. So really, you can trace this idea at least to the year 1958. That's about 60 years ago. Or 70? A lot. 60. So this was actually a proposal to deal with imprecise MDP models in inventory management. Back then, computers had like 15 kilobytes of memory. We didn't really have any data. So this technique didn't really take off. It was a little bit ahead of its time. There was a little bit of work on the topic in the 70s. Then a bunch of work under all kinds of different names in the 90s, competitive MDPs, bounded parameter MDPs. And the stream I'm going to talk about is this one, rectangular robust MDPs, which were proposed in mid-2000s and have been studied quite a bit ever since. Now, if you're interested in a broader view of this topic, I'm going to recommend this textbook called Robust Optimization from 2009. It's getting a little bit out of date, but it's a beautiful book which will walk you through all the techniques. All right. So we talked about these general ambiguity sets. And we know that solving this robust problem for them is NP hard. So what we're going to do, we're going to make some assumptions to simplify this problem. So in the general setting, I'm constraining my nature across all states and actions. So the first type of a model I'm going to talk about is called S or state rectangular model. And in this model, their nature is now constrained for each of my states individually. So instead of having one constraint that's across all the states, I'm going to have one constraint for each state. And this problem is going to be tractable. Can anybody guess why? This is a very general principle in MDPs. All right, I'll tell you. It's because of Bellman optimality. Anytime we have something that is defined over each state independently, we can use Bellman optimality, we can use value iteration. So this is called an S-rectangular model, and I'll show you a little bit later how you actually solve this. There's another model called SA rectangular, or state action rectangular. And in this case, we're defining our constraint for each state and action independently. And while the former model, you can interpret as nature seeing the state, but not seeing your action, this one you can interpret as the nature seeing both the state you're in and the action you took. Now, can anybody guess why this problem is easy to solve? Any guess is a good guess. It's the same reason. Bellman optimality. Not all my questions are trick questions. Okay, so what I mean by Bellman optimality. But maybe before I get there, this is the question I actually get most often. The question is, why is this called a rectangular set? What does it mean state rectangular, state action rectangular? What are the rectangles? This is what the rectangles are. If you look at the state action rectangular ambiguity set, and you look at the set of possible transition probabilities across one state and another state, this is going to be a rectangle. Similarly, if you look at the ambiguity set across one action and another action, this is always going to be a rectangular for the SA rectangular set. Always. It's because our constraints are defined independently for states, for different states. Now, for S rectangular ambiguity set, you're still going to have a rectangle across different states, but across actions, it may not be a rectangle anymore. Question? Right here? So the question was, what is the difference between the methods from what you're optimizing? So in the S-rectangular case, you apply your constraints for each state independently, but then the constraint is across multiple actions from this state. Okay? That means that the nature gets to choose an action, but has to the nature chooses the noise, but it has to choose the noise without knowing what action you're taking. In the S-rectangular case, you're assuming a nature which is more powerful. The nature gets to see the state you're in and can respond to any action you take with a different kind of noise. All right, so in this case, the nature is constrained for each state and action independently. So you can really see this robust MDP as a game. Yeah? Sorry, question.
Nature is more powerful in the second setting. I mean, it seems like it's constrained to pick the noise in a more regular approach. As an adversary, it's constrained to pick less choices.
So the question is, that's a very good question. So the question was, why is the SA rectangular nature more powerful than S rectangular nature? kind of seems counterintuitive. The way to think about it is the S rectangular nature only sees your state, doesn't see your action. So it has to commit to the noise before it knows which action you're taking. The SA rectangular nature is more powerful because it gets to see not only the state, it sees your action. And so depending on which action you take, it can choose a different type of noise. I'll show you another example, which will hopefully make this a little bit more clear. Are there other questions? So this is one way of looking at this robust MDP. It's like a game. It's a game that you play against the nature. So you have a state, you take an action, and the nature now chooses your transition probability, and that determines which state you go to and how much reward you get. So think of it as a specific type of a zero-sum game against an adversarial nature. Now, I'm not going to go into details with this topic, but you can further ask whether your nature is static or dynamic. A static nature is going to pick the same transition probabilities every time you visit a state. That means once it introduces some kind of error to some state, it has to use that same error every single time you come to that state. So it's static, it doesn't change. Another option is that the nature is dynamic. Nature can change what it does every single time you visit a state. Now, Adam told you about policies. It turns out that in robust MDPs, the picture is a little bit more complex than in regular MDPs. So there are 2 or 4 types of policies. Your policy can be history dependent, or it can be stationary. It can be randomized. It can be deterministic. And it turns out that if the nature is static, the nature doesn't change. Your optimal policy is not going to be the kind of policy we usually see in RL. The policy is going to be history dependent. It's going to be history dependent because every time you visit a state, you learn something about what your nature did. And then you can learn, you need to change your actions based on what you saw in the past. Now, surprisingly, if the nature is dynamic, that is history dependent, nature can change what it does in every state. And if you were willing to compute history dependent policies, then the optimal solution is actually going to be stationary, both for you and the policy, and the nature. So for state action, rectangular robust MDPs, the optimal policy is stationary and deterministic. For the state rectangular policies, we'll see an example, and the optimal policy is stationary and randomized. Any questions? Yes?
So do you think of the dynamic case as a fun MDP or another MDP at all?
To be honest, I haven't spent much time thinking about the stationary case, the static case, and as far as I know, nobody has, because it's a difficult problem. But I think that's a very interesting research topic. You cannot model this as a POMDP. You cannot model this as a POMDP, but it's similar in spirit. It's like a robust POMDP, which actually there are some papers on, but it's super difficult. It's really hard to solve. All right, so let's look at how we solve these robust MDPs. So we've seen the Bellman optimality in regular MDPs. Hopefully all of you are familiar with this. If we have state action, rectangular ambiguity sets, we can formulate almost an identical optimality equation. So what we're seeing here is we're choosing the best action. The nature is choosing the worst case transition probability. Here the delta is the set of all valid probability distributions. And instead of using a fixed p, we are using the p that's chosen by nature. And this is our constraint. Now I'm using an L1 norm. You can use basically almost any distance measure in this equation. So very similar concept to regular optimality in MDPs. Things that get a little bit more complicated for the S rectangular case. For the S rectangular case, we are now not choosing an action, but we're choosing a distribution. Because remember, we need randomized policies. So we're maximizing a distribution subject to a constraint that now spans over actions for your individual state. So here you have a different constraint for every action. Here you have one constraint for all the actions in the state. Are there any questions? All right, good news. I have some good news. This robust Bellman operator is very similar to the Bellman operator in MDPs. What does it mean? That means that it's a contraction in the alpha-D norm and is monotone element-wise. This really means that you can take the same value iteration that you like for MDPs and essentially use it unchanged in robust MDPs. Now, you can also take policy iteration and apply it to robust MDPs. I actually did this myself for many years, and it seems like it should work. And it works most of the time, but not always. Turns out that's not a good algorithm. It's an algorithm that may not converge, may loop forever. And I put a citation here from the 1990s, which actually shows you that taking a policy iteration as it is, applying it to robust MDPs, you can end up with a cycle and never get to the optimal value function. And as I said, there's no nonlinear programming formulation for the robust MDP problem. So, as long as they are rectangular, robust MDPs are relatively easy to solve. So let's see how well it works. So the same problem we looked at before. This is our optimal nominal policy. This is the policy I showed you before, which makes $8,000 if things are as we expect them. When things are SA, when we add SA rectangular ambiguity set, we lose $8,000. If it's S rectangular, we still lose about $8,000. And really, if the policy is deterministic, you are not going to benefit from less powerful nature, a nature that doesn't see your action. If you solve a robust MDP, things are quite a bit better, right? So you go from 8,000 to 7,000 if your model is correct, but you're only losing $27, which is still a loss, but it's not too bad, right? But still, the SA robust and S robust are going to give you about the same solution. And if you look at what the policy does, it switches to the more powerful pesticides earlier on and actually gives up a little bit earlier on, because we're trying to mitigate the uncertainty. And so you give up just a little bit in terms of your solution quality if your model is correct, but you get quite a bit of an improvement if your model is wrong. This is just the transition probabilities. And this is what happens if we compute the S rectangular policy. Now, as I told you, the policy is going to be randomized. And so what I'm showing you here is the distribution over the different actions. And now because the nature can make one of your, the nature really needs to make all the actions that you're randomizing over really bad. And so your solution is going to be much better. And even in the robust case, you're still making $4,000. So the things are pretty good. Are there any questions? Yes?
So the way these like rectangular constraints and noise will translate into change in return, like in some number.
Yeah.
It's also a property of the environment itself. So I wonder if there's a way to characterize the environments and say, like, for example, for this kind of environment, we really need to be robust, and for this kind of environment, it doesn't really matter.
Very beautiful question. So the question is, what are the environments where robustness matters, and what are the environments where the robustness doesn't matter? Very good question. I think there should be research done on that. There hasn't been any. I think that's a very important question. So let's talk about a little. I'm not going to go into details here, but I want to tell you a little bit about how you actually solve this, because I didn't really give you the whole picture. So another question. We have this robust Bellman optimality. We want to compute the best action and the worst case transition probabilities, right? Now, we know how to compute the best action. You have 10 actions. You try each one of them. You pick the best one. Now, here, P is a continuous variable. You need to optimize it over some polyhedral set. How do you compute P? What do I say? What is the generic method you can use to solve robust problems? Linear programming. Yes, easy. Linear programming, as a theoretician, this looks really nice, right? It's polynomial time. It's great. We solve the problem. We formulate it. But now let's go and see if this is really tractable. So I have a very simple benchmark problem with 200 states, 200 actions. It's this inventory optimization problem. I look how long it takes me to compute a Bellman update. It's 0.04 of a second, so pretty quick. I now formulate this as a linear program, use Gurobi, which is a very powerful, very expensive linear programming solver. Costs about $50,000 to buy. And I go from 0.04 seconds to 16 minutes in this case to solve one state update. This is not good, right? Now, if my students see a problem like this, they always come and ask for a bigger computer or more computers, right? And I always tell them, maybe you just need to think a little bit harder. So don't leave yet. This doesn't mean that you cannot solve the robust MDPs. You just need to be a little bit more clever. And it turns out that for many of these models of ambiguity, there is a better way. I don't have the time to actually go into the details, but this is a table which summarizes for which metrics you can compute this in quasi-linear time, which is really, really quick. There's some references. Many of these techniques have been reinvented. This one, I know at least 5 different original works that derive the same algorithm. And we actually have some unpublished results here, which we can also solve in n log n time. I unfortunately don't really have time to go into the details how you do this, but the basic idea is to take advantage of some simple hidden properties of these problems. And just to show you how well this works is if we put everything together, this shows you the computational complexity as it grows with the number of states. Here you see where Gurobi reaches the 5-minute cutout, and here you see The MDP, it's 600ths of a second, and this is about a factor of 5 worse. So it's a little slower, but you can still solve really large problems almost as easily as MDPs. Any questions? Have we solved the problem? Is this it? Is this all we need to care about? We add a little bit of noise. Is there something missing here? Yes, something is missing. I am not going to, I'm not going to cover this, but I'll leave this here. I'll make the slides available. You can look at some extensions of the rectangularity. So there's this big fundamental question. We can compute a robust solutions when we have a model of small errors, right? But what is a model of small errors? So let's look at some options, right? So we looked at our optimal nominal policy. We're not doing any robustness, right? And we know that if we don't add any noise, we make a lot of money. When we add a little bit of a noise, we lose a lot of money. When you add a bit more noise, we lose a ton of money, a lot of money. Not a good solution, right? We can add a little bit of a noise, right? We don't make as much money if there's just a little bit of a noise in our model. We just lose a little bit of money. But if there's quite a bit of noise in our model, we're still losing a lot of money. All right, so let's optimize for 0.04. A lot of noise. We optimize, we want to be very robust. What is the problem with this solution? Would you want to deploy something like this? You're always losing, you're hedging really well, right? But you're always losing money. So that's not really the right answer. So which one of these do you want to optimize for? This is not really the only question, right? So what is the size of the ambiguity set? Should our size be the same for each state and action? Should some states be less uncertain than the others? I use an L1 norm. Is that the right answer? If it's robust with respect to L1, is it robust with respect to L infinity or KL divergence? Which rectangular to use? SA as rectangular, which one is better? So really, this is going to depend, I believe, on the reason why our models are wrong. So we need to start to dive a little bit deeper into the actual way you'd use this in reinforcement learning, and what is it that makes your models wrong. So let's see how this would work. So I told you we're interested in this batch RL, where you simply get a data set. An example is a data set like this. This is a logged result of a very good policy. Here you see the population, the actions, and you want to learn from something like this. So I generally think of this dyna-like setting with a single iteration. So this is something Martha talked about really nicely yesterday. We'd follow this step. We collect data, use machine learning to build some kind of a transition model. Then we solve the MDP, and we deploy our policy, cross our fingers, and we hope it works. Okay? The model can be wrong. Why can the model be wrong? What do you think? What are the main reasons why a model constructed this way may be wrong in reinforcement learning? Not enough data. Good answer. the transition model is not precise. So the model is simplified. This could be aggregation. This could be value function approximation. This could be a bunch of other reasons. We call these models because it's not reality, because they simplify reality, right? Models are always wrong. Sometimes useful. Some people think they're never useful. Any other reasons? Sorry? Yes, the data can be biased. And I think this is a very important topic in RL. So in RL, you're generally, in batch RL, you're getting a data set from one behavior, and then you're recommending you change the behavior, which is going to introduce covariate shift to your data. So these are the main reasons I've been able to think of and that people have considered. So model simplification, value function approximation, simplified simulator, limited data, where we don't have enough data, non-stationary environment. So we may be learning on one environment, but the environment may be changing. So this paper has looked at a case where you're trying to balance the cart pole, and the pole is getting longer or shorter. And your observation can be noisy. And what I argue is that each one of these sources requires a different treatment. And I don't have the time to cover more than one of them, and I'm going to focus on this problem of your data set being limited. So what is the general big picture approach? Instead of just building a transition model, we're going to build a transition model and some measure of confidence. Some measure that's going to tell us how good our model works for different states. Then instead of solving an MDP, we're going to solve a robust MDP, which accounts for the confidence. And then we can deploy this policy and sleep well, because if we do all our math correctly, we can be confident that our solution is good. So say you're using a data set like this. I tell you, tell me what's a better policy for managing this particular pest from a data like this. What do you notice about this data set? It's uniform. Like uniform?
I mean, it doesn't have a sharp peak.
It doesn't have any sharp peaks. So what can you learn from this data set? I picked this because this is actually very common in the types of data set that I get to see on the problems I work on. So you see these actions. I told you there are 5 actions. You only see 4 of them ever in your data set, because they never use the strongest pesticide. You can learn from this model how well each one of these pesticides works, but how well does it work when the population is 40? Can you learn that directly from this data? No. Is this common? Yes. No farmer is going to let you just, hey, don't do anything. Let's see what happens if you're just not spraying, if your population destroys your crop. No. They're going to, they send you away. They tell you to go away and never come back again. So you need to figure out what happens in these other populations based on this limited data, but you want to also account for the fact that you don't have any data for that mode. You need, this is a place where you want to account for your uncertainty. All right. So just to show you a little bit more of a formal way of thinking this problem, the common objective for thinking about this is called the percentile criterion, where you decide on some kind of a confidence level delta, and you want to compute a policy that's going to guarantee that your return is greater than some y with the probability of 1 minus delta. So this is like a 90% confidence interval. You're not trying to get 100%, because 100% is never going to be possible. You're going to allow for some probability of failure, but you want to do well. Now, another way of looking at this is that you are being risk averse with respect to epistemic uncertainty. If you don't understand what I just said, don't worry about it. But if you do, that's great. This is value at risk. P star is the random variable, and this is your return. So why is this a good objective? It's robust. This gives you a guarantee. So if your policy is not going to work, you'll know. You'll know because your y, your robust solution, is going to be really low. Once you get a policy, you're pretty confident that when you deploy it, you're not going to do worse than what you expected from your optimization. So you know when you fail. This is very important. The general approach to this is you construct your ambiguity sets such that they give you a guaranteed lower bound with the probability of 1 minus delta. So like 90% probability that when you solve your robust MDP, you're going to get a lower bound on the return. Now, how do you actually address this? So this is a bit more complicated than DINA, because we're trying to not only compute a model of transitions, we're also trying to compute or quantify how confident we are in these transitions. So there are two big, broad approaches to this. One is taking the frequentist framework, which makes few assumptions. It's easy to optimize. Unfortunately, some people might argue with this, but it's really too conservative and probably useless in practice. It doesn't generalize. What I'm a fan of is a Bayesian framework. Now, a lot of people say it's not good because it needs priors. I think that it's good because it can use priors. So you can supply additional information as priors. It can be computationally demanding, but it also gives you good generalization. Now, I put these on the same slide. What I really want to emphasize is that 90% frequentist confidence is very different from 90% Bayesian confidence. They give you completely different types of guarantees. So that's something to be aware of, and there's a reference where you can learn more about it. I'm kind of running low on time. I'm going to skip this. If you want to know more about happening inequalities, I'd be happy to talk about that offline. How do we use these Bayesian models? So there is a simple approach where we start with a Dirichlet prior for every state. We see some samples. We get a Dirichlet posterior. We sample from that, and we get some result. That's quite limited because it can't generalize. What I'm a fan of is parametric hierarchical Bayesian models, where we inject our model with some priors, some structured priors. And this is actually very, very common and popular in the ecological modeling literature. So we are saying that the population at t plus 1 is some alpha times xt, population at time t, plus beta times population at t squared, plus some Gaussian noise. This is not the real model. This is just an illustration of how you construct a model like this. Then you can use MCMC to sample from the posterior. This is what it looks like for this data set that you saw before. I'm a big fan of these tools that I don't see used as often as they might be in our community. Stan, JAX, PyMC3 for Edward, so on. Very powerful Bayesian modeling frameworks. You don't need to really implement or know much about MCMC to get very powerful generalization from simple models. And this is your posterior distribution, where the red line is the true mean next population, and this is the posterior sample. So here you see exactly that from your data you have quite a bit of confidence about the low population state, but you don't really know what happens when the population is high. And that's, you're really going to be trying to trade off the uncertainty with the possible gain. There's some cool results here, which I unfortunately don't have time to go into, but again, I'd be very happy to talk about it. The bottom line, this is one of the more surprising things that I've ever come across, is if you want 90% confidence in your solution, constructing the 90% confidence region, it's really called credible region, is the wrong thing to do. This set is too large. All you need is this little tiny set in the middle to get your 90% confidence. It's really simple, very surprising. It's a lot of, there's some technicalities that I'd be happy to get into offline, but don't really want to get into here. And if you compare this, this is the same population model. No surprise, the Bayesian methods are going to work much better than the non-Bayesian ones. All right, so just some other approaches. I'm not going to go into details here, but I'm going to make another version of the slides available where there's more details on this. So I try to sell you this robust objective where we're solving for maximum policy, minimum pi and r, so a simple max-min problems. But there are some very interesting and important variations on this framework. So you could try to instead minimize the robust regret. And I think this is a very good objective. In many problems, this is perhaps the right objective. You care about how much you lose with respect to the best you could do. You generally get quite different solutions than in the robust objective. Most people don't solve this, not because they don't want to, but because they don't know how. This problem is NP hard for almost any interesting case of ambiguity sets. Another work is if you have a baseline policy, you want to improve on this policy. You want to make sure that you fall back to your baseline policy if you are in a part of the model which is uncertain, and improve your policy if you have a good model. And then you want to solve this. You want to minimize this baseline regret. Unfortunately, it's also NP hard. It's NP hard for rectangular ambiguity sets. It's NP hard for all kinds of other ambiguity sets. Some people solve it. We don't really have good ways of solving it that may or may not matter to you. So I've run out of time. I'm going to just summarize what I said in 3 slides, and then I'll be out of here. So message number 1, robustness matters in RL. I feel like we don't spend enough time talking about it. We don't spend enough time trying to make this better. If I were to say why, is because if you don't have a simulator, you can't do cross-validation. You don't have a test set. How do you know whether you're getting a good solution? This is especially important if the cost of failure is high. One approach to this, which I think is very promising, is to use robust MDPs. It's a flexible, convenient model for robustness. They are well understood by now, easy to use, tractable, not much harder to solve than regular MDPs. And to use them, we need to learn both the model and the confidence in this model. I spend most of my time talking about model-based methods. There are a couple references here for taking very similar approach to this problem using model-free approaches. And finally, to just give you some future research directions, what I think is very important is first scalability. So I showed everything in a tabular case, which a lot of people may find not so interesting. Now, a lot of the ideas that I described here generalize to value function approximation. The problem is that you lose a lot of the guarantees. You lose a lot of the guarantees, which you may or may not care about. Rectangularity is one of these things that we generally use because we can solve those problems, not because it is always the right framework. And so we need to understand how we can relax this assumption and preserve tractability. And I think we need to do more applications in RL to really make an impact and see what is it that we're missing, see where our methods work. All of the results, all of the demonstration here, all the code is online. This is actually a pretty well-tested library for robust MDPs, but it's unstable. It's not well documented. Use it at your own risk. One day, it may be well documented. I'm not sure when the day will come, but you can have a look at that. And I'm going to stop with that. Thank you, everybody.